Hi everyone, I'm Jakaran. Today we'll be discussing what are coroutines and how we can actually use them. What are the advanced features of coroutine? What are the internal workings of coroutine? How we can actually configure coroutine. So let's get started. There are a couple of definitions which I have actually copy pasted, which I have copy pasted from Wikipedia, and I have copy pasted from one of the blog by Snarky Canadian. So coroutine are computer program component that allow execution to be suspended and resumed. That allow execution to be suspended and resumed. Similarly, generalizing subroutine for cooperative multitasking. You don't bother yourself with what are these terms, what do they mean. We will discuss them further in this discussion. They have been described as function whose execution you can pause. So there are a couple of key takeaways from this particular slide. The number one thing is coroutine is something which we can actually suspend. Coroutine is something which we can actually resume, whose execution can be resumed, whose execution can be suspended, whose execution can be resumed. Coroutine are something which would use the principle of cooperative multitasking. Cooperative multitasking. Similarly, we have ability. You can pause them. So we have ability to suspend them. We have ability to resume them. So we have the ability. So these are the four takeaways from what are coroutines. Coroutines are programs whose execution can be suspended, whose execution can be resumed, which works on the principle of cooperative multitasking, and we have the ability to pause their execution, suspend their execution, and resume their execution. So how the coroutine works? Let's take an example of a coroutine which is executing on a single thread. So there are multiple coroutines which are executing. Let's say we are executing C1, C2, C3 in our on a single thread T1. So when we are executing multiple coroutines on a single thread, what happens? C1 is actually executing. What happens? C1 have a delay function. Delay function is nothing but a timeout function of 5 seconds. Let's say. So we are simply saying ki we are using a delay or a timeout function or for C1, or C1 might have a IO request for which it has to wait for a response from a particular downstream service, or or might be it is waiting for particular event to happen before executing part of its program. So C1 might be using a delay function where it is waiting for a timeout of 5 seconds. It might be waiting for a downstream response, IO request is there, or it might be waiting for event to happen. So C1 part of C1 gets executed, then it has to wait maybe either for delay for IO for event, and then part of C1 executes. So this is how the coroutine C1 is. So this is a part one of coroutine. This is part two of coroutine. So part one of coroutine gets executed on this thread T1, but it enters into a waiting phase for delay or IO or event. Then it enters into a suspended state. C1 goes into a suspended state where it says I don't need any CPU resource or any resource for 5 seconds. So what happens where this threads it becomes free when coroutine gets suspended. This thread becomes free and it starts executing another coroutine C2 on a same thread when C1 enters into a suspended state. C2 gets executed, it gets completed. Again, C1 is still in suspended state. It will start executing C3, and when C3 gets completed, C1 enters into the resumption state. It will be pulled back on this particular thread and gets executed completely. The part 2 of C1 will get executed. So this is the basic concept of C1, where it's where not concept of C1 but the concept of coroutine, where coroutine which is being executed on a particular thread can get suspended when it enters into a waiting state where it says it don't need any thread for its execution, or it don't need any resource for its execution. It can enter into a suspended state, and other coroutine can utilize the same thread, and thread doesn't have to wait with coroutine for IO request, for event, or for delay timeout. So thread is free to execute other coroutines, and this is better optimization of thread resources. This is simple concept of coroutine. So there are a couple of takeaways on this slide. The first thing is the execution order is always sequential. We started executing C1 first, then C2 got executed, then C3 got executed, but C1 here isn't completed. So after C3, C1 again got executed. So the execution order will always be sequential. However, order is not maintained. Execution order is not maintained. Order is not maintained, but it's always sequential. Execution of coroutine is always sequential. There is no parallelism. No parallelism. Similarly, it is always sequential. There is no parallelism involved. So there is no concept of locking, no concept of mutex, and so on. Okay. So, however, we see the execution order is not maintained, and the it gives the impression that all the tasks are executing simultaneously. So it gives the impression of concurrency. It gives the impression of concurrency. So these are the key takeaways from this particular slide. So this is how coroutine actually works. Coroutine actually works, and so coroutine has ability to get itself suspended. So as we see, the coroutine gets suspended so that other coroutine can actually come up and utilize the same thread. That's the basic and core concept of coroutine. So we will discuss what are the difference between when we say multi-threading and we are going for a coroutine. So what is the difference between them? If we go for a because the thread concept is also similar to this particular coroutine concept, where we say that multiple threads are being executed, and various programs are being executed on various tasks are being executed on multiple threads. So what is the difference when we say thread versus coroutine? What is the difference between two? So when we say threads versus coroutine, the first point which we want to note here is coroutine is cooperatively multitask and thread is preemptively multitask. So if let's say we have n threads being executed at the same time, and we have X core machine where x n is greater than x. So let's assume n is 100 and we have 10 core machine, x is 10. So we know at a same particular point of time only 10 threads would get executed in on a single core. On the 10 cores, 10 thread actually be executed. So there is an external scheduler is needed. What it will do, it will say, let's say it has given 10 threads 1 second of CPU time. Then scheduler will come, it will say, hey, give other threads chance. So it will interrupt the existing thread and give other 10 threads 1 second chance to execute on CPU. So there is external scheduler which is actually interrupting the execution of these threads. So threads are interrupted to let other threads execute. This is preemptively multitasked. However, in coroutine, they are not interrupted. They willingly give up their execution. So we saw in earlier example when C1 is entering into a delay function, or is entering into a IO request, or is waiting for an event, it will give up its execution and will itself enter into a suspended state. And so C2 will get to know that the C1 has entered into suspended state, thread is free, now let me execute. So it is cooperatively multitask. No one is coming and saying C1 to enter into suspended state. It willingly enters into a suspended state. However, in case of thread, we have to interrupt the thread. Thread actually provide parallelism. because multiple threads are executing on at a same particular point of time. However, we saw in a case of coroutine there is no parallelism, as they are being executed one after another. So however, they can enter into a suspended state. So we have seen there is a there is a concurrency there. However, no true parallelism is available in coroutine because they are executed one after another. No two coroutines get executed on a single thread at the same time. This is not happening. This is not happening. However, multiple threads get executed at the same time on a single machine with multiple cores. So this is it gives concurrency, not true parallelism. So no mutex needed, nothing needed. Also, yeah. So no true parallelism is there in case of coroutine. So how to use coroutine? So there are two ways to use coroutine. We can simply use launch keyword in coroutine. We can use async keyword in coroutine. Launch keyword, what launch do? It's similar to runnable in Java, and async is similar to callable. It launch doesn't return any value. Callable returns some value after its execution. So launch returns some doesn't return value. Async returns value after its execution. Let's look into the code examples. So this is a particular blog which I have written. You can actually access this blog, thejoyzindagi.com/blog/8, and check out this blog as well. So here is an example of launch. Of what there are three lines which we need to execute coroutine. First, we need to set up a context. Context is actually being there are default contexts available in Kotlin, but here we haven't used any default context. We have set up our own context with a thread pool of 30. After setting up a context, we need to set up a scope, or coroutine scope. When we have coroutine scope, we can launch a coroutine in that particular scope. So this coroutine, which actually does nothing but does a execute a print statement, is launched in this particular scope, which has a context of this thread pool, 30 thread pools, a thread pool having 30 thread. This is here we have used a launch keyword, and this everything is similar for the async. Async, the only thing is it will return a value. It will return a value. So we'll look further more into what is the context and what is the scope, and what are the various values which we can provide. But this is a basic implementation of coroutine, where we want to launch a coroutine based on our own thread pool. If we don't want our thread pool, what we can simply do here is we can simply use dispatcher.default. This context which we are using here, we can simply use, instead of this particular line, we can simply use dispatcher dot default. That is a context, and that can be used, that's a default context which has been provided by Kotlin. Similarly, there are two other contexts which are provided: dispatcher.main, dispatcher.io. Basically, IO is more optimized for IO request. Main default are more optimized for CPU request. So, this is what we are currently. This is how the default dispatches, which are default contexts which are available, or and we can use them by dispatcher.io, dispatcher.main, dispatcher.default. Okay, so when we want to use our own thread pool, we can simply use our own thread pool by saying executors.new fixed thread pool. We have created our own thread pool, and there is extension function which has been provided by Kotlin as coroutine dispatcher. It creates a context for us using that particular thread pool. After creating a context, we need to set up a scope, and after setting up a scope, we can launch thread pool via launch in async. Okay, so we already have discussed that there are three types of inbuilt dispatchers or context available. We can simply use them. If you want to see the example, here is example. While launching, I simply said dispatcher.main. That's how it is being used. I have provided while launching. I have provided the context here. Context can also be provided before executing launch or async by this particular by using a scope. Okay, so and how the question comes up ki how are we suspending a coroutine? Coroutine execution is good. We are using this particular program to execute coroutine, but again, how can we actually suspend coroutine? Coroutines can be suspended if we tell them to suspend. It is a cooperative multitasking. So coroutine itself has to tell that it wants to get suspended. No external scheduler is coming up and saying ki hey, you need to get suspended. Other coroutine are waiting in line. That's not happening. So coroutine can tell to get itself suspended by using a suspend coroutine keyword. The block inside suspend coroutine gets executed before coroutine gets suspended. So what happens here? The execution will enter here. It will enter. It will see suspend coroutine. What will happen? It will execute this particular part, this particular piece of code, and then this coroutine will get suspended. Okay, what happens when coroutine gets suspended? So coroutine save the task state because it's actually running. There might be some other code after this particular suspend coroutine. So it will save the task state for current task state. It will return the thread it is using to the thread pool, back to the thread pool. It will run after, not after execute method, but restore thread context method. It will execute restore thread context method, not after execute. Restore thread context method if it has been implemented in thread context element. We will just see it. So we'll look into it. What is it? But take it as it is. It will save the task state. It will run restore thread context method of thread context element. If it has been implemented, it will return thread to the thread pool. So how to trigger it back? Again, it has no suspended. Now there is no way to trigger it back, as we can see here. So when we actually go and suspend coroutine, we provide a continuation object. Here the continuation object has been hasn't been explicitly mentioned, but here it has been mentioned for detailing purpose. So when we are suspending a coroutine, it provides us with a continuation object, and this continuation object can be passed to in any event, or it can be passed to any thread, or it can be passed to any method, downstream method. And from there, when we feel need to resume this particular coroutine, we can simply call continuation object dot resume. This is what we need to do to trigger it back. That's it. Now when we resume the coroutine, because we have seen we are already using a thread pool, already using a thread pool here. So there are multiple threads which are being executed, with multiple threads available, and over these 30 threads we are running coroutine. So what coroutine will do? Coroutine will use these particular threads to get executed. Coroutine will use these particular threads to get executed, to execute itself, and any available thread will be picked up. So when we resume coroutine, any available thread will get picked up. Okay, it is not exactly the same particular thread. So it simply pulls any available thread from the pool and run the task. And if we do not suspend any coroutine, and we simply say we are running 30 coroutines simultaneously, and we are not suspending any coroutine, then each coroutine will pick up a new thread from this particular thread pool and will execute itself. So all 30 threads will be used to execute all 30 coroutines. And if we suspend any coroutine in between, that thread will become free and will be returned back to thread pool, where it could be picked up by another executing coroutine. This is the basic working of coroutine. Now we have seen there is something as thread context element. So what happens is sometimes we want our programs. We have a coroutine which we want to run. We have a coroutine which we want to run. But before running coroutine, we want to set the thread state. And after coroutine has been executed, we want to restore the thread state. Restore thread state. So we want to set the thread state. We want to restore the thread state because why we want to set the thread state, because the coroutine which will be executed need that particular thread state to get before execution, or it could be a thread context which we want to set, not exactly a thread state but maybe a thread context which we want to set before executing coroutine, which is very common when we have uh, we have parallel programming. So which is common where we want to set a thread state. Similarly, when when we are completed and we this coroutine has completed its execution, or we are putting it in a suspended state, we want to restore the thread state so that it could be used again. This thread could be used again for other coroutine execution. So that is for coroutine, we already know we have provided a block where we have a coroutine program or code or logic there. But how can we provide set and restore thread state or thread context logic or code to this particular coroutine that can be accomplished via thread context element? If we look into Kotlin definition of thread context element, it simply provide two methods: update thread context and restore thread context. We just need to implement these two methods to set the thread context to restore the old thread context. After implementing these two methods, this thread context element can be provided in the scope. So here we see this has been provided in the launch, and if we go back to our program, the other way to do it would be while providing a scope, coroutine scope, here context plus thread context element. So it would be something like this. uh, if I write the program here, it would be something co- coroutine scope. In coroutine scope, I would be simply providing the context which I have created above plus thread context element. Thread context element. This is how it is being provided. As you can see, currently we are only providing the context, not the thread context element. But if we have thread context element implemented, we will simply plus that and the implementation of the thread context element. So every if we provide it within the scope, and anytime we trigger async or launch within that scope, this thread context element, two methods, that is update thread context and restore thread context, will be executed before and after coroutine is uh, uh, is executed. So this is invoked before coroutine is resumed on current thread. This is invoked after coroutine has been suspended on current thread. Hope this has given you a good insight into coroutine. Please feel free to comment, and if you like the video, hit like button and subscribe to my channel. Thank you.